All right, guys, this is our third video on Monday, March 23rd. And we're going to start by analyzing this spectrum right here, especially since I've got a typo. So let's fix it right away. So this should be C3H6O2. Okay, so calculating our degrees of unsaturation. So an alkane with 3 carbons would have 2N plus 2 hydrogens. So 2 times 3 is 6, 6 plus 2 is 8. So for our degrees, we've got 8 minus the 6 that we have. Oxygen has no effect. Divide by 2, that gives us 1 degree. Now thinking about what 1 degree means, double bond, a ring, we only have 3 carbons. Ring is not very stable, although not impossible. But we do have oxygen, so let's check for that 2-ish region, which we have. So next to a C double bond O. Now, a lot of people, again, want to think what we did earlier. We've got 2 oxygens. What has 2 oxygens? Well, we've got a carboxylic acid. Okay, so let's check for that. This would be, right, at 11 to 12, there's nothing there. So we can get rid of that. Okay. Now, some people think about an ester, which we did before and it worked great, and we're going to try it and see if that works for us again. Okay, this region should be next to a carbonyl, which is that 2-ish region. Yeah, we've got a signal there. Now, this region right here would be that 3 to 4-ish region. Okay, we do have stuff here, but we have kind of 2 in that area, which is a little interesting. So we're really going to have to think that one through. Okay, we only have, let's see, 3 carbons. Okay, so how is that actually going to work? Okay, so let's give it a shot. Okay, let's try an ester. Okay, we only have 3 carbons. So if we put our CH3 there, which is consistent with this one, our singlet having 0 neighbors, that's a good fit. Have 0 equivalent neighbors. Okay, so that's good right there. Now we already used up 2 of our carbons. We need our oxygen because we're trying out an ester. We want this more downfield area there. We only have 1 more carbon to branch. That would be our total of 3 carbons and 6 hydrogens. Now the problem with this structure, and you can probably already see it, is, all right, this looks okay. This would be in that 3 to 4-ish region because we're next to electronegative oxygen. These guys have no neighbors, so this would have 0 equivalent neighbors. So that would be a singlet in that 3 to 4-ish region, which we have. But what about this third signal? So this only has 2 signals. It can't be an ester. We have 3 signals. So it's great to check your work. We ruled out that this is an example, even though we're used to these splitting patterns here, not splitting patterns, but chemical shifts being of an ester, we've got 1 more signal. So we can't have an ester functional group. We're going to have to break up our oxygens. We're good. We definitely know we have that carbonyl, but we have to move our oxygen because we've got another signal there. So what are all those things in here? Okay. We have ethers, the ROR, okay, but we don't have enough carbons. We only have 3 carbons to do that. We also have alcohols. So how can we do that there? We're going to have to break things up. So we're good with this part. Okay. This was set in stone. This is super helpful. We only have 1 more carbon to deal with, okay, and 1 more oxygen. We just can't put the oxygen coming off of here. So let's put another carbon coming off of there. Now we're done with carbons. We only had 3 to begin with. Okay? And then if we need to put our oxygen on there, well, we're going to have to put a hydrogen on it. There's no more carbons to use. And then, of course, we need to finish filling in our octet for our carbon here. We'd have a hydrogen and a hydrogen. That would be a CH2 group. So that's the only other way we could break up our 2 oxygens and only work with 3 carbons. So let's check our splitting patterns here. This, again, is our singlet. And that's around 2-ish, which we have. Again, a singlet means we have 0 equivalent neighbors. There are no neighbors here. Now, these 2 hydrogens, some people go, well, they do have 1 neighbor. So an alcohol, I'm going to put a star next to it, is just like an aldehyde. Okay? We've got these lone pairs here that sort of act as a barrier, okay? Just like in an aldehyde. Okay, so this is, again, I'm going to say similar to an aldehyde. Okay, again, an aldehyde looks like this. And this hydrogen here, he doesn't feel any neighbors on an adjacent carbon here because of that carbonyl wall. This is like a barrier. So these electron clouds are sort of like a barrier. So it's pretty rare that an alcohol hydrogen feels any of its neighbors, and these hydrogens won't feel the effect of that hydrogen on their splitting pattern. So when we go through and label, we can say these hydrogens here have 0 neighbors. We're not counting that hydrogen, and there's no hydrogens here. So this would be a singlet. Okay? And it's more downfield. Some people go, well, why isn't it at 2? Because it's next to a carbonyl. It's also next to an oxygen there. Okay, so that's what you're seeing right here, that purple signal right there. Okay, and then this little guy, he's super de-shielded. Okay, just being stripped of its electron density, being directly attached to that electronegative oxygen. This would be our little OH alcohol in here. Again, fitting our chemical shifting in that 3 to 4-ish region where we see halogens and ethers and alcohols. All of that's in there. And he would be a singlet. So we've got our 3 singlets all where we want them to be. So let me flip just 1 second. And we're going to do, you're staring at Grandma's carpet as I'm locked in a bedroom. Let's take the time to go back and look at some things that we keep seeing in lab, our IR spectrums. Now we have our NMR spectrum, and here they're giving us a little bit of our mass spec information. So now is the time to get caught up. You're still required to know your wave numbers for your different chemical bonds in IR spectrum, which we do in lab all the time. Now we've been learning NMR, and of course you're still going to be using some mass spec, so make sure you pull out those notes. Go back over different cleavages, homolytic, heterolytic cleavage, what is a molecular ion? All of those things are going to keep coming back at you, so you need to make sure that you keep reviewing them. So we're going to label some things here. Says, what does the IR spectrum indicate possibly? We're not labeling everything to a T, but what sticks out at you? Okay, so most of us are very familiar with this big stretch right there. Look at the number 1700. So right away, everyone should have said that that is a C double bond O. We know we have a carbonyl. If you take a peek at your spectrum, you do have that carbonyl region right here. So that matches, right? Next to a C double bond O. So I'm going to put that on there as well. Okay, not too sure about any of that. I don't know, is it an aromatic? Is it not? Because a lot of people are like, oh, 14 to 1600, I'm going to label everything as an aromatic. I don't have a formula, so I can't check my degrees. I can check my NMR. There's nothing in that 7-ish region, so we don't have an aromatic. And then we do have our carbon-hydrogen stretching. It looks like it's at 2900, so probably our sp3, carbon-hydrogen stretching. Okay. And we do have alkyl area right here. Okay. And notice we've got 2 different splitting patterns next to a carbonyl. Okay. So we're just dealing with a carbonyl. We don't have any other oxygens, things like that. So we need to think of, okay, what might have a carbonyl? So we've got 2 structures. We have aldehydes, and then we also have our ketones. Okay. Now an aldehyde hydrogen, this little guy right here, he's always 9 to 10 ppms, right? A singlet that's 9 to 10 ppms on an NMR. There isn't anything there. So we don't have an aldehyde. We're dealing with a ketone. Okay. And again, these stretches right here, this would be around 2-ish ppms. This side would be around 2-ish ppms. And notice we do have 2, right? There's 2 different signals in that 2-ish region. So probably for the 2 different sides of our ketone. Okay? So let's label these splitting patterns here. Remember, this is our solvent, probably our TMS solvent or some other solvent that they use. Okay, so we're not looking at that. So this is a common triplet that we always see upfilled. And what does a triplet tell us? Well, a triplet means these hydrogens that are giving this signal have 2 equivalent neighbors. Okay? So how do we get 2 equivalent neighbors? That's like if I had a CH2 next to me there. So again, typically, that looks like a CH3 next to a CH2. So we could say these hydrogens have 2 equivalent neighbors. Okay, so that's kind of what we're thinking about. And again, we've got to figure out what else everything's attached to. Now we've got 2 signals here that should be on either side of our carbonyl. Here is that singlet that we're used to seeing, which means we can't have any neighbors. So these hydrogens that are next to a carbonyl have 0 equivalent neighbors. Sorry, getting a little smushed. I'll draw a line between the 2 right there. Okay, so again, this singlet right here means these hydrogens have 0 equivalent neighbors. So what does that look like? Well, we know it's next to a carbonyl, and we've seen a few times before, again, hydrogens next to a carbonyl will have no hydrogen neighbors. So that would give us that singlet that we're seeing there. And then if you count down here, we've got 1, 2, 3, 4. We have our quartet. Okay, so what does a quartet mean? It means these hydrogens have 3 equivalent neighbors. Okay, so the hydrogens that are giving this signal have 3 equivalent neighbors. We already have that piece of the puzzle. These hydrogens have 3 equivalent neighbors, and of course they need to be next to a carbonyl. So what does that potentially look like? Here is our singlet that we have in that 2-ish region next to a carbonyl, and then of course we need the other side of a carbonyl. Here's our CH2, and they need to have 3 neighbors to give a quartet. So these guys right here are that quartet. They have 3 equivalent neighbors. 3 plus 1 is 4, giving us a quartet. So we match. Again, these guys would be our quartet, right around 2-ish. These guys are our singlet, right around 2-ish. And then our group here, that's a little more upfield, that is our triplet in that 1-ish region. Okay, so we're working with our ketone. We've got two signals, both in that 2-ish region for the two different sides of the carbonyl, and then that triplet that we see in a lot of our structures for that upfield alkyl group. Now just a little review here. It says your mass spec indicates a 43 AMU fragment. Show how it was formed in the cleavage of your molecular ion parent. So we already know the structure of our molecule. Now in a mass spec, your molecule gets bombarded with a high energy electron beam. That's going to eject a lone pair easiest first. So if we're looking at our molecular ion parent, remember it's got to be a positively charged fragment, we would have lost one of those electrons from oxygen before we lose them anywhere else. Now, because this molecule is now unstable, it will undergo a lot of different cleavages. Cleavages of carbon-hydrogen bonds, carbon-carbon bonds. We've got this radical here, so we can do our homolytic cleavage. And we need to figure out what is our 43 fragment. So let's practice our homolytic cleavage. So in homolytic cleavage of a carbonyl, we're going to end up breaking these adjacent carbon-carbon bonds. And we've got two different sides. Okay, so let's just start with one. If this one electron moves in, it needs a partner. So we could try it from here. And then this would end up here. So notice we're forming that triple bonded fragment right there. So now we've got a triple bond to our oxygen. Oxygen still has that lone pair. Oxygen still has a positive formal charge. Okay? And then we still have this methyl group attached. And then this group that broke off is now our radical. And remember, radicals, their weights are not recorded in a mass spec, only positively charged fragments. So if you add up the weight of this thing, we've got 2 carbons, so 12 and 12 is 24. Oxygen weighs 16, so what's 24 and 16? That's 40. And then add 1, 2, 3 for your hydrogens. This is our 43 AMU fragment. That is resonance stabilized. So that positive charge can be shared between carbon and oxygen. So we would expect that peak on a mass spec to be pretty intense. Okay, so just a little review there. So keep practicing, you guys. We're going to be starting a new chapter soon. I'll let you know which one that is in a little bit. But this week, your goal is to continue working on your spectrums throughout this packet. We're going to be having a quiz very soon on NMR, so I will give you a heads up about when that is. Of course, it's timed and it will be scheduled during normal class time, so make sure we're sticking to that. While you can watch these videos anytime, any tests and quizzes will be scheduled at our normal class hours, so that's really important that you keep that open. I will talk to you soon. Gotta go import, export, and upload all of these to our YouTube channel. Talk to you later. Bye.